Higher Notes, Unit 2, Section 7, Emission and Absorption, Spectra. And this is part 1, where we'll look at irradiance. So we're going to begin by imagining a flat two-dimensional area A, a certain number of meters squared. And following on to that imaginary area, we have light evenly covering the whole of that area. And that is shown in the diagram by the blue arrows, indicating light incident on the area and falling perpendicularly on that area. So that's light energy. And we define irradiance, quite simply then, as the amount of power arriving on the area in the equation. Irradiance is power divided by area. So it's the number of watts per square meter, basically. In symbols, that becomes I is P over A, where P is the power of the incident light in watts. A is the area in meters squared upon which the light is falling. And capital I is the irradiance. And of course, if you look at the right-hand side of that equation, power divided by area, watts divided by square meters, that makes the irradiance equation watts per square meter. One thing to watch, irradiance is symbolically represented by capital I. There's a small possibility you could confuse that with electric current I, although it's pretty unusual in the problems we do that should be the case. Let's have a look at an example then to see how the equation works. So, light from a lamp falls upon a screen of area 2.5 meters squared. If the power of the beam is 0.025 watts, find the irradiance of the light beam. So, we set up our equation. Irradiance is power over area. Put in our numbers, 0.025 watts spread over 2.5 square meters. And we get an irradiance of 0.01 watts per square meter. So fairly simple to use, and that equation is on the list. Now in this part of the course, one of the learning outcomes is an experiment which you need to know and remember and be able to describe. And it's one you will have seen. It's an experiment to look at the variation of irradiance with distance from the light source. And here's how we do it. Well, we begin with a lamp. It's a small bulb, in fact. And we need a light detector. And that light detector needs to be connected to some sort of meter. You can get versions of this where we have a Bluetooth connection from the detector to an iPad as well. There we go. And we need to measure the distance between the light source and the detector. And that would be done with a meter stick. Now, whenever you're drawing experimental diagrams, it's important that you show every piece of apparatus that's being used, even simple things like meter stick, and that you label all the important apparatus pieces as well. So this, for example, is a bulb. This is a light, an electronic light detector. And I've labelled the meter already. That's a meter stick. And a crucial measurement in this experiment, of course, is the distance between the light detector and the bulb. So we'll call that distance D. And the meter and light detector obviously help us measure the irradiance that is being detected. Well, that's the apparatus. What we do is we basically switch on the bulb. We keep it at constant brightness, that's constant voltage, and we gradually move the light detector from a close position further and further away, maybe going further away in 2 centimetre steps, right up to maybe 50 centimetres or thereabouts, and we record the corresponding irradiance each time. Then, as you would expect, we plot a graph, and when we plot a graph of irradiance against distance, you'll see what happens. We get something like this. So, in this graph, we have distance D in meters on the x-axis and irradiance in watts per square meter on the y-axis. And what you find is that your graph does this. So it turns out that the irradiance is directly proportional to 1 over d squared. This is a classic example of an inverse square relationship. Basically, as the distance increases, the irradiance decreases quite rapidly. And inverse square relationships, where one quantity is directly proportional to 1 over the other quantity squared, that's the inverse of the other quantity squared, these are quite common in nature. Now, it's a curved line, it's awkward to work with, so we prefer in physics, as I'm sure you know, to get nice linear relationships, because they're just mathematically easier to handle, more convenient. So what we do is we replot the same data. We still have irradiance on the y-axis in watts per square meter. But this time we plot 1 over d squared, and that of course would be in meters to the minus 2. When we do that, we get a linear relationship, a straight line, doing something like that. And that's generally more convenient to work with, because when you look at that, we can say that the irradiance is clearly directly proportional to 1 over d squared. In other words, y is directly proportional to x. It's the same relationship as above. but it's now in a linear form. And rearranging that, we can say that I equals some constant k times 1 over d squared, where k just is some constant. That follows from the mathematics of direct proportion. Notice I've moved from a relationship to an equation there. An equation is a specific type of relationship. Now it's easier to actually write that by bringing the d over d squared over, and you get that id squared is equal to a constant. So for any given light source of fixed brightness, the irradiance times the distance squared will always give you the same number. So if you move to a different distance, your irradiance drops, your distance goes up. But when you multiply I by d squared, you always get the same number. And what we usually do is we usually say, okay, so let's imagine we have I1 d1 squared, so it's a particular distance d1 from the light source. And at that particular distance, you'll get a particular irradiance I1. But if you then move to a new distance, you'll get a new irradiance. And that new irradiance, I'll call I2, will always equal the new distance d2 squared. So that's the equation we tend to use. This equation here is the one that you'll find on the equation list, but in solving problems, I would use the I1 d1 squared is equal to I2 d2 squared version. It's just an awful lot easier. Okay. Right, let's do an example. The irradiance of a lamp is 0.01 watts per square meter when light is detected 3 meters from the lamp. Find the irradiance (1.5 meters from the lamp. So we're 3 meters away to begin with, and the irradiance is 0.01, and we're moving closer in. We're only 1.5 away, that's half the distance. The question is, what's the new irradiance? Well, you should expect the irradiance to be greater closer in, because if you go back to your graph, you can see the smaller the distance, the bigger the irradiance. So here's how we set these out. Now, it's quite important to set these out in a systematic way, and the best way is to list your variables in a before and after format, a little bit like you perhaps did with the gas laws in 4th year with P1, V1 and P2, V2, etc. So you've got I1 and D1 as your before variables, and then you've got I2 and D2 as your after variables, after you've made the change of distance. So our original irradiance is 0.01 watts per square meter, and our original distance is 3 meters. The new irradiance, I2, after the change of distance is unknown, but the new distance is 1.5. Now if you set it out like that, it becomes quite straightforward. Then you say I1 d1 squared equals I2 d2 squared. Put in your numbers. Rearrange for I2. Again, don't round until the final line. And when you work all of that out, you'll find that the new irradiance is a larger number, in this case 0.04 watts per square meter. And that's how you use the irradiance equation. This brings us to the end of this short note on irradiance. That's 2.7, part 1.